Assalamu alaikum. My name is Hafiz Waleed Zahid, roll number 21 TE83 from Telecommunication Engineering Department UAT Texas. Today we perform Lab 6 of Digital Signal Processing, TFT Properties and FFT. Here this is a task 1. So we have a code. In this code, the function frequency decimation takes two inputs, signal 1 which is the input signal and n which specifies the length of a discrete Fourier transform. The DFT of the input signal is calculated using the FFT function with the length n. This results in the frequency domain representation of the signal stored in the variable x. The magnitude spectrum and phase spectrum of the DFT are plotted in separate subplots. The frequency components are decimated by keeping only the first n by 2 elements of the DFT. The signal is reconstructed by taking the inverse DFT of the decimated frequency components using the IFFT function. The reconstructed signal is plotted in a separate subplot. This function provides an example used by defining an input signal and specifying the length of the DFT as n. The function frequency decimation is then called with these inputs. This is the main code and this is the output of this code. In task 2, this MATLAB code iterates through a set of a given signal and corresponding the lengths of discrete Fourier transform, comparing the DFT results obtained from a custom function frequency decimation with those from MATLAB's built-in FFT function. For each signal, it displays the signal plots and magnitude spectrum, phase spectrum, and reconstructed signal using the custom function, and then prints the calculated DFT using both the custom function and MATLAB's FFT function. This comparison allows users to verify the correctness of the custom function outputs against MATLAB built-in function for computing the DFT, aiding in validation and testing of the custom implementation. In task 3, this MATLAB code defines two signals x and y, computes their discrete Fourier transform using a custom function validate decimation. This function likely calculates the DFT, plots, and magnitude phase spectrum and reconstructed signal. The script then compares the results obtained from the custom function with those from MATLAB's built-in FFT function for both signal x and y. This comparison enables validation of the custom implementation against MATLAB standard functionality, ensuring accuracy and reliability of the custom DFT calculation for the given signals. Additionally, it aids in understanding any potential discrepancies or differences in the results produced by the custom function compared to MATLAB's implementation. This is the output of the following code. In task 4, the provided MATLAB function calculates the discrete Fourier transform DFT of a signal x using a custom function named myFFT. The result of the DFT denoted as x is then displayed using the DISP function. However, without seeing the implementation of myFFT function, it's challenging to provide a detailed explanation of how the DFT is calculated and what the frequency representation x represents. If you provide the code of the myFFT function, so this is the output of the following code. In the last task, the provided MATLAB code calculates the fast Fourier transform FFT of 4 given signals W, X, Y, and Z using a custom function named myFFT. 4 signals Y, X, W, X, Y, and Z are defined with different lengths and values. The FFT of each signal is calculated using the custom function myFFT. The results are stored in variables W underscore FFT, X underscore FFT, Y underscore FFT, and Z underscore FFT. This code displays the comparison of FFT results between the custom function and MATLAB's FFT function for each signal. For each signal, it prints the FFT results obtained from the custom function and MATLAB's FFT function. In this code, the result of the custom function FFT with MATLAB's built-in function, the script allows verification of the correctness of the custom implementation. Here is the output of the signal of the given code.